Alright. Okay, so question number 37. In an experiment, Jovan placed two identical beakers containing the same amount of water at room temperature on two trays of ice as shown. So I tell you, all these things are very important. Room temperature. Room temperature is important, especially if they state room temperature is for a reason. So room temperature is about 25 degrees Celsius. We usually take it as shown. Okay? Now, then they go on to ask, which setup X or Y would the temperature of water drop faster? Explain why. So basically, when you see temperature, you know that this is a concept of topic on temperature and heat, correct? So drop faster. So drop faster in this case indicates that there is some form of heat transfer. So in this case, they are testing you on heat transfer, right? Rate of heat transfer, in fact. So you need to talk about how heat is being lost or gained at a faster rate or lower rate. Okay? Now, so they are talking about water. Explicitly, water. So in the two setup, right, if you take a look at it, okay, you know that your water, alright, is of a lower temperature than your block of ice. So technically, heat will be travel from your water to your block of ice this way. Okay, this will also happen in the same scenario. Now remember, I told you this. Whenever you've got two setup, you need to compare and contrast the difference. So the difference between these two setup is that one has gaps in between. Okay, now a lot of you think, okay, that this question has got to do with air being a poor conductor of heat. But no, people, listen. If you take a look at here, the air, right, the point that is gaining heat, right, is from this region to this region. And the point of contact is here. In between, there is no air. There is no air between the ice cube and the beaker. If there was air in between, yes, then you can say that the air acts as a poor conductor, therefore heat loss from the water to your ice cube will slow down. No. So this question has got nothing to do with air being a poor conductor of heat, because the air is not in between the 2 points of contact, your two regions, A and B, which is your water and your ice cube. I stress again, the air is not between the two regions, right? So technically, heat doesn't flow through your air. So therefore, they're not looking at air. What are they looking at? They're actually looking at amount of surface area in contact. So if you take a look at these two, this one, okay, would have a smaller surface area in contact. With the ice, right? Okay, because it's just here only. Whereas this one over here has a greater, the water has a greater surface area in contact with the ice, right? So because this one has a greater surface area, there is more surface area for heat to be lost from the water to the ice. So therefore, temperature would drop faster in this setup over this setup. So in this case, what am I looking at? Okay, I would say that, okay, my answer is actually setup X. Why? So I must talk about the surface area, right? So there was a greater surface area in contact with the ice and beaker of water. In X then Y. Now, be very careful. A lot of you actually wrote exposed surface area. I don't know where's the exposed. Can you please tell me where's the exposed? Your English is atrocious. Okay? You can use exposed when it is talking about the surface area of, like, say, water to the surrounding air. But if I were you, I wouldn't want to use exposed. I will make sure I talk about, water in contact with the surrounding air. That will be very, very clear. Okay? So, because of the difference in exposed surface area, heat would be lost from where to where? From the water to the ice faster, resulting in the temperature of water in X dropping faster. Okay? So once again, the common things, when it's a heat loss, from where to where. Okay, and because it's a comparative kind of question, you have to use superlative, faster, greater. All this needs to be there. Next. Jovan then placed bottles of tea in a tub of ice cubes as shown below. Using the findings from his experiment, suggests what he could do to cool the bottles of tea more quickly. So as you can see, what happens is that the lesser or the more the surface area in contact with the ice, the faster it will cool down, right? So what you can do is you use crushed ice instead. Okay, because crushed ice, you can then cover more surface area. Okay? Use smaller pieces or crushed ice. Or you can say you pour water to cover it. That will work because the ice will cool down the water, and then the water will actually have a greater surface in contact with your bottles. Next. Okay, this question. Now, the diagram on the right shows the top view of a pinball machine. Okay, the plunger is put back from here, pull back, so it goes all the way here to propel the ball, okay, into the play area. The player scores more points if the ball hits the bell on its way into the play area. Okay, when the plunger is put back to position P and released, the ball hits the bell. Explain in terms of energy changes. Why is this so? Okay, so energy changes tells me that this is an energy conversion question. So what I need to do is, I need to first find out what kind of energy is converted to what type of energy. So this is an energy conversion question. So now, so what happens is that they say start at P, right? So you need to first tell me, okay, what type of energy is being possessed when it's put back. And that will be your elastic potential energy. Correct? Your elastic potential energy. So when it's put back to here is elastic potential energy. And then when you release it, okay, the potential energy in the spring is converted because it's moving. When it's moving, it is kinetic energy. Now, take a look. The trajectory of this is that it goes up. Okay? And then after that, as it goes up, it's gaining what? It's actually gaining GPE. right? So you have to talk about GPE. Your kinetic energy as it goes up is being converted into GPE in order to hit your bell. Okay, because you need GPE later on so that when it falls back down, okay, it has GPE to be converted to KE to touch the bell. Alright? So how will your answer look like? Okay, when the plunger is put back to P, the spring is compressed. A lot of you did not mention this. Because it's compressed, right? Hence there is, okay, elastic potential energy in the spring. So when the plunger is released, the potential energy in the spring is then converted to kinetic energy. Okay, right? You think about it, that allows it to move in the ball. Remember, you must always tell me kinetic energy of what? Potential energy of what? Okay? Which is then converted to what? This, in turn, is converted to more GPE in the ball, allowing it to hit the bell. Okay? Now, then they ask you, the bell is then moved to position R. It is observed that the ball could not hit the ball when the plunger is put back to position P. Suggest what could be done to the plunger so that the ball is able to hit the bell at R. Give a reason. Now, this question, a lot of you tell me, oh, compress the spring more. Hello? The question already tell you that it's already to P. P is the maximum level it can go to already. How can you compress it even more? You can't. So the whole idea is, if it is at a higher position, you will need more kinetic energy to get it to the top, right? Okay? So how do you do that? You obviously need to backtrack. How do you get more kinetic energy? You need to get more elastic potential energy, which is from your spring. So the only way you can do that is to increase the elastic potential energy of your spring. And one way to do that is to use a stiffer spring. Stiffer means that the spring, okay, you need to use more force to push it down, to compress it. So because more force is needed to compress it, it means that it will have more elastic potential energy. You got it? That is the first way. The second way is to use a longer spring. So with a longer spring, once again, to get it back down, you need to use more force. So two methods. Either use a stiffer spring or use a longer spring. Don't tell me use a less elastic spring. It's not the same. It's not the same. I stress again, I'm putting this on video. Do not say that. It is not the same. Elasticity has got nothing to do with stiffness. We're looking at stiffness. So what can you do to increase the elastic potential? You can two methods. Okay? Either you use a longer spring or you use a stiffer spring. Only these two answers is accepted to increase elastic potential energy. More elastic potential energy in the spring when compressed to position P. therefore more elastic potential energy to be converted into kinetic energy in the ball, which is converted to more GPE in the ball. So you realize that this and this, the answers are very similar, okay, because it is an exact translation. The only difference is because you increase your elastic potential energy, therefore you will also increase your kinetic energy, and then you increase your GPE. Now it's very important to tell me elastic potential energy in where? In the spring. Kinetic energy in where? In the ball. Gravitational potential energy in where? In the ball. Same thing as your waterfall question. Your electricity generating question. You have to tell me what the energy possessed is by what item. Very important. Okay, and the superlative. Can you see more, more, and more? Next, the diagram below shows how a car traveling on a road moves a short distance after the driver steps on the brakes for the car to come to a stop. This is called braking distance. Okay? Julia conducted an experiment to find out how the type of surface affects the braking distance of a car. She rolled a rubber ball over 4 different surfaces. So straight off the top, without even looking at anything, I already know this is my change variable, and recorded the time taken for the ball to come to a stop as shown in the graph. So basically, my recorded time here is my measured variable. And then I think about it. Come to a stop. Time taken. What does it translate to? Actually, straight off the top, I already, at the back of my mind, I should get some form of understanding. The longer it takes means less friction between where? Tires and surface. Right? Because less friction, right? Because friction works in the opposite direction. So if it takes a longer time to brake, okay, or it travels to a longer distance, it means that friction is less. So how does this help me? So when I look at the graph, I can make sense of it. Okay? So for example, if I look at A, wow, A is actually the one that has the most friction. Because, oh wait, is it? Wait, let me think. Traveled by the ball. May not be, because it took the shortest time, but it also traveled the longest distance. Right? But when I compare it to D, wow, D over in this case, okay, it basically took the longest time. Okay? And traveled the shortest distance. So this tells me that because it took the longest time, okay, what it means is that, okay, the friction in this case would be, okay, the greatest. Right? Okay, so based on the graph, which surface A, B, or C would the braking distance of the car be the shortest if the car traveled at the same speed? Explain why. So your answer would be D. Okay, because in this case, if you look at D, okay, the ball took the longest time, okay, to travel the least distance. That means it's very slow. There is a lot of resistance. Okay, there is a lot of resistance. Okay, can I backtrack a bit? I think I misunderstood this part. So I'm going to backtrack a bit over here. Yeah, Let me re-explain this part. Okay, and recorded the time taken for the ball to come to a stop. Meaning that if let's just say a ball has more friction, it should come to a stop faster. Okay, because friction stops things from moving, right? Okay, so basically, okay, the longer the time that it takes for it to come to a stop, it means that it's actually less friction. Okay, my apologies. Okay, because if something has more friction, it should take less time to come to a stop. So therefore, if you look at the graph again for D, so because it actually took the longest time, okay, the longest time to come to a stop, okay, as well as the shortest distance means it's the slowest, okay, it means that the amount of friction was the greatest. Okay, so your answer would be D. The ball took the longest time to travel the least distance. Okay, so this you're quoting your evidence here. So I give you the most amount of time already. Can you see? Wow, I give you 30 seconds but you only travel what? Up to 2 meters only. So that means friction must be very great, must be the greatest. You're very slow. Something must be acting against you, right? So your ball is going this way, friction is going this way. Okay, so therefore you are slowing down, and therefore I give you the longest time, but yet you are the you traveled the least amount. Okay. Hence, this suggests that the friction between the ball and the surface was the greatest. Okay, next. Okay, state 2 variables that Julia need to keep constant for the experiment. So the 2 variables that she'll need to keep constant will be force applied on the ball. Okay, and the second one would be mass and size of ball. Very straightforward. Okay, C. Now, suggest how the snow chains help drivers to be safe. Okay, now think about it in this way. You know, ice is slippery, right? You want your car to basically not slip off the road. So you want to increase friction. Okay, so once again, very simply, snow chains increase friction between the ball and the surface of the icy road, therefore preventing the car from sliding off the road. Okay, the last part is actually important because it tells you how it makes it safer.